Welcome back, students, and we are about to begin a new unit here. This one is about chemical compounds, Unit 3. Here are some of the topics that we're going to be covering. We're going to start talking about different kinds of compounds, and particularly we'll spend a lot of time talking about ions and ionic compounds. And then in a later part of our section here, we will consider how do we arrive at the empirical and molecular formulas of compounds. All right, so let's get started. Remember that elements can combine with other elements to form compounds. This is different than a mixture. A hydrogen-oxygen mixture can have any proportions of hydrogen and oxygen gas. Water, by contrast, is composed of molecules that always contain 2 hydrogen atoms to every 1 oxygen atom. In other words, water has a definite proportion of hydrogen to oxygen. This is what helps us classify it as a compound. Now, when 2 or more elements combine to form a mixture, you have a mixture, and the properties of the mixture may or may not reflect the substances that are in there. But when 2 or more elements combine to form a compound, an entirely new substance results. The compound's properties are typically different from the properties of the individual elements. This table shows you, for example, selected properties of hydrogen, oxygen, and then water molecules, which is the compound that is made between hydrogen and oxygen. Notice that at room temperature, hydrogen and oxygen are both gases. And if they were to be liquefied, they would have very, very, very small, very low boiling points. Water, on the other hand, at room temperature is a liquid with a high boiling point. Flammability. It's interesting. Hydrogen will combust. It explodes if you expose it to a flame. Oxygen is necessary for combustion. In other words, no oxygen, no flame. And then water, we use it to essentially extinguish fire. So it's very interesting, the properties of water, the compound, versus the properties of the elements that make it up. To represent compounds, we use chemical formulas. The chemical formula is going to indicate the elements that are present in the compound and the relative number of atoms of each. In some cases, it'll be ions. So for example, as we know, water is represented by the common formula H2O. Sodium chloride, which is the name for table salt, is represented as NaCl. When we look at the array of compounds in nature, we can classify them into two large categories, ionic and molecular compounds. Let's spend some time here talking about ionic compounds. First of all, remember we talked about how in many cases atoms or groups of atoms will gain or lose electrons, resulting in the formation of an ion. So ions have an unequal number of protons and electrons. Don't forget, we make ions by changing the number of electrons, not the numbers of protons. Let's consider a lithium. Lithium is a metal with atomic number 3, so it would have 3 protons and 3 electrons with a 0 charge, and we call it lithium. The lithium ion, on the other hand, which we represent with an Li and a positive superscript in there, would have still 3 protons because it's the same atomic number, but it only has 2 electrons, leaving an imbalance of charge that results in a +1 net charge. We call this the lithium ion, and for ions that carry a positive charge, like lithium ion, we call them cations. Here's another example of a cation, calcium. Atomic number 20 would have 20 electrons in the neutral state, but in the calcium ion, it has only 18 electrons for a net charge of +2, and you can see how it is represented here on the left as a calcium with a superscript 2+. We can also have negatively charged ions. Fluorine, atomic number 9, would have 9 protons and 9 electrons for a 0 net charge, but the corresponding ion actually has 10 electrons for a net charge of -1, and we call this the fluoride ion, and we represent it with a superscript above the atomic symbol of a negative sign in there. Atoms that gain electrons to produce negatively charged ions, these ions are called anions. Here's another example for oxygen. Atomic number 8 would have 8 electrons in its neutral state, but it actually forms what is called the oxide ion that has 10 electrons for a net charge of -2. Once more, we represent that with the symbol of oxygen and a superscript with 2-. Notice that we don't write it -2. We typically write it 2-. So in general, the way we name ions depends on whether you are starting from a metal or from a non-metal. So cations are produced by metals, and we name them the same as the metal. You just add the word ion to it. So for example, sodium, represented here as a process in which it's losing an electron, it results in the sodium ion. Calcium would lose 2 electrons, resulting in the calcium ion. Now, with anions that are made from an element, from an atom of an element, we simply change the ending of the name to the IDE form. So fluorine would gain an electron to form the fluoride ion. Oxygen would gain 2 electrons to form the oxide ion. Now there's a special category of metals. As we will see, metals will typically form positively charged ions, in other words, cations. But some of them actually form more than one kind of ion. And to represent that, we write a Roman numeral in parentheses to indicate the charge of that particular ion. Here's the series for iron. Atomic number 26, so in the neutral state, it would have 26 electrons, but it has the possibility of forming 2 different ions. One of them has 24 electrons for a +2 charge. The other one has 23 electrons for a +3 charge. Notice that the symbols on the left are used to represent the ion, but if we want to say the name of the ion, we would call the one with the +2 charge iron 2 ion, and the one with the +3 charge, the iron 3 ion. And notice the Roman numerals. If you've forgotten how to write Roman numerals, don't worry. I think the highest we're going to go to is 4. So please just review how to write Roman numerals 1, 2, 3, and 4. Okay, don't worry about it. Now the question you would ask is, why would these elements form ions in the first place? Well, remember that we said that in nature, one of the big measures of, that we check is stability. And for some reason, the noble or inert gases, those that belong to the group 8, are very stable. And when we say stable, it means that they are stable towards chemical reactions, chemical changes. For some reason, the arrangement of the electrons in the atom makes them very stable. And so because of that, these elements do not form ions. They do not form compounds. They stay as monoatomic species. That's single atom, right? Now, let's say that that is the more stable state for an atom. Then we can see here where other elements would quote-unquote gain stability by having an electron arrangement similar to that of their closest noble neighbor. It's hard to see on the periodic table because the separation between, for example, some of the metals in groups 1A and 2A and the noble gases seems very, very pronounced because they're on opposite sides of the table. But remember, the table is a way of representing actually a sequence that is based on the actual atomic numbers. What if we were to see the periodic table as like a multi-level parking structure with ramps? You go down one level, and when you reach the end, there's a ramp that goes to the next level. But actually, it doesn't go straight up, but it kind of zigzags back. Another way of looking at it is to look at the periodic table in this form, like a spiral. Okay, so let's look in this case here. Let us consider, for example, chlorine. I'm going to see if I can get my marker to work here. I guess not. Let's see if I can use a different color for my marker here. Okay, here we go. Let's use this one here. Here is chlorine. Okay, notice that on the regular periodic table, chlorine is on the kind of like right side, or what I've called sometimes the northeastern part of the table. Notice that chlorine is right next to the noble gas argon. They're only different by 1 electron. So you can see how chlorine would rather get 1 more electron and have the same number of electrons as argon, some kind of magic number that makes it more stable. So it explains why elements like chlorine, fluorine, sulfur, oxygen, which are closer to the noble gases, would benefit by gaining electrons, right? Now, let's see what would happen if instead of that we would consider a metal. Let's consider some metals now. All right, and I'm going to use a purple color for this. Let's consider now the element sodium. On the periodic table, sodium is on the left side of the table and all the noble gases are on the right side of the table. It seems like the distance from sodium to helium, neon, or argon is the same. But notice that in this spiral representation, sodium is right next to neon. They're only different by 1 electron. However, in this case, the way that sodium could have the magic number of electrons that makes it stable would be by losing an electron to have 10, and that's why sodium would form a +1 ion. So if you continue this game here, you can see where we can arrive at some patterns here. Let's look at the patterns. Group 1A elements, which are called the alkali metals, would form +1 cations. Just go down that column and see how convenient it is for them to just lose 1 electron to become, the same number of electrons as the quote-unquote nearest noble gas, which you cannot see from the grid representation of the periodic table, but you were able to see here using the spiral representation. Group 2A elements, the alkaline earth metals, would form +2 cations. Now, with the nonmetals on the right side of the table, you can see where the group 7A, the halogens, would form -1 anions. Group 6A, that's the group that has oxygen and sulfur in it, would form -2 anions. And group 5A, that would be the group that has nitrogen and phosphorus in it, would form -3 anions. Notice that this is for those elements in those groups that are nonmetals. The exceptions, well, the transition metals, even though they do form cations, do not fall into this kind of a pattern. So we are going to have to deal with those kind of individually. Let's look at this table here. It shows you what we call the monatomic ions. And technically here between you and me, you're supposed to kind of drop that O there if to follow correct rules of grammar. But I kind of like monoatomic. It kind of reminds me that what I mean by that is that these are single atom ions. Okay, here we go. Group 1A, you can see them here. They form +1 ions. Group 2A, +2. Group 7A, -1. Group 6A, -2. Group 5A, -3. Carbon forms what we call a carbide ion that has a -4 charge, but the chemistry of those compounds belongs to a different field, and so we're not going to be considering those. One of the things that's important is to realize that we have these groups of ions here that actually form more than one kind. Now, I am not requiring you to memorize what those ions are, but what I need you to know is if you look at the symbol of a metal, I need you to realize, hey, this is one of those guys that can form more than one ion. Now, right now, the way I taught you how to do the names of these ions is by writing the name of the metal followed by a parenthesis and the Roman numeral that corresponds to the charge. In the old days, these ions had a different way of naming them. For example, the iron 2 ion would have been called the ferrous ion, and the iron 3 ion would have been called the ferric ion. So if you're looking at, for example, iron supplements, let's say, for example, women who are taking prenatal vitamins, the supplement might say something like iron 2 gluconate or iron 3 gluconate. I forget which one they use. It won't say that. It'll say ferrous gluconate or ferric gluconate. In the pharmaceutical industry, they sometimes still use the old style of nomenclature, but we're going to use the new one, all right? Okay, now, here's the thing. Ions are charged particles. We don't expect these things to exist out there by themselves because in nature, things tend to form stable arrangements. So what these ions will do is they will pair up in order to neutralize the charges. So positive with negative, okay? Don't forget, equal charges repel, opposite charges attract each other. And that is how ionic compounds are formed. It's a compound that is formed when cations with positive charges and anions with negative charges interact. Many of these compounds are sometimes also called salts. So we call salt a specific type of ionic compound, sodium chloride, but in chemistry, many ionic compounds are called salts. Now, how do you tell from either the name or the formula that a compound is ionic? Well, what you do is if it has a metal and a non-metal, it is going to be most likely ionic. How do I know that? Well, I'm going to use the periodic table, and I showed you in Unit 2 how to distinguish which elements belong to the metals, which ones belong to the nonmetals. The thing that holds cations and anions together is the attraction between the positive and negative charges. But here's what's important. When they combine, they have to combine in a proportion that results in zero net charge. In other words, every positive charge has to be balanced by a corresponding negative charge. We're going to call the electrostatic attraction between oppositely charged ions an ionic bond. Notice that in the world of physics, this is simply what we call electrostatic attraction. It's a force, it's an electrical force, but we're going to call them ionic bonds. And the result of these ionic bonds is what's called an ionic compound. Now, the ionic compound is going to be solid, first of all, and it's going to be composed of a lattice, which is a regular three-dimensional array of alternating cations and anions. Kind of like this. If I could look at a very, very, very tiny sample of a salt crystal, I would see where the sodium and the chloride ions are arranged in this very highly ordered format. Notice that there is no such thing as a molecule of sodium and chloride ions. It's just a three-dimensional array that in any sample will have zillions of these atoms. The important thing is that whatever size sample you take, there's always going to be one sodium ion for every chloride ion, and they're going to be organized in this way. So when we write the formula for the ionic compound, since the compound exists as a crystal lattice of ions and the number of ions in total depends on the size of the sample, we don't try to represent the actual numbers of each ion. What we do is we take advantage of the fact that the net charge has to be zero. That means that the charges on the cations and anions must cancel one another. This is the case even if we take the compound and dissolve it, for example, in water. The ratio of cations and anions stays the same. So the way the formula is written is so as to represent this ratio of plus to minus charges with the smallest whole numbers. Remember, in the array of the crystal lattice of sodium and chloride ions that we have in salt, we have 1 sodium for every chloride. Therefore, the formula we write is NaCl. In other words, sodium, 1 sodium for every chloride. Okay, let's practice here. Here are 4 different sets of ions, and I want us to write the formula of the ionic compound that forms between A, sodium and fluoride ions, B, calcium and oxide ions, C, aluminum and chloride ions, D, sodium and sulfide ions. So this is going to require some skills, but the basic strategy is determine what is the charge expected on each of the ions, and then decide how many of each will be required to produce a neutral compound. For this, we're going to go to our paper board, and we're going to do these exercises on paper, and then we'll come back.
Okay, we are going to work the formulas of these ionic compounds here on paper. So let's start out with A, sodium and fluoride ions. The first thing to do is to find out what kinds of ions are these two going to form. Let's write down the symbol for sodium, and let's write down the symbol for fluorine. Now the sodium ion, of course, what we do is we look at the periodic table and we see that sodium is in group 1A, which means that it's going to form a +1 ion. Fluorine, or the fluoride ion, they are in group 7A, and as you can see, they should be 1 removed from neon, which means it's going to want to get 1 more electron and form a negatively charged ion. So the question we ask is, for every sodium atom with 1 positive charge, how many fluoride ions with 1 negative charge each would we need? It's obviously a 1-to-1 ratio, so our formula is written with the cation first and the anion second, and there we go. Okay, let's go ahead and do number B. In this case, we have calcium, Ca, and we have oxide, which is the ion of oxygen. Again, you look at the periodic table. Calcium is a group 2A element, so it's going to form a +2 ion, but we write it 2+ as the superscript. And oxygen is over here on group 6A. It is 2 groups removed from the noble gases, which means it wants to gain 2 electrons. So the oxide ion should be 2-. And the question is, well, how many units of each do we need to get a 0 net charge? And yeah, the answer is 1 of each. So we'll write the symbol, or the formula, so to speak, as CaO. Okay, let's go here, number C. And this is aluminum and chloride ions. Chloride comes from chlorine, which is Cl. Again, we look at the periodic table. Here is chlorine. Again, just like fluorine, it's 1 column removed from the noble gases, so it wants to gain 1 electron. Aluminum, on the other hand, is over here, kind of right in between, but it is a metal, so you have to ask yourself, what is, easier? To gain 5 electrons, to have 18 like argon, or to lose 3 and have 10 like neon? Well, as a good metal would do, it loses electrons, but it now has a 3+. So now we have a situation where each aluminum ion requires 3 charges to be neutralized, but each chloride ion only brings 1. So that means that we need how many? 3, right? So that means that for every aluminum unit, we're going to need 3 chlorides, and so we're going to put that as a subscript over here. And that's the formula for this compound formed between aluminum and chloride ions. Okay, let's do the last one here. This will be between sodium, and we already know from our first exercise here that it's +1, and sulfide ions. Well, sulfur is in the same group as oxygen, so it'll have the same charge in its sulfide ion. It'll be 2 negative, right? So the question now is, how many of each do I need? Well, the sulfide requires 2 charges to be neutralized, but the sodium ion only brings 1. So that means that we're going to need 2 sodiums for every sulfide. Bear in mind as we write these formulas that essentially what the formula is telling me is what is the ratio of one ion to the other one in the overall compound. And we'll talk about this some more later. Well, as chemists many times do, we like to find shortcuts. We like to simplify our lives. Since the idea here is to find ratios of ions that will offset each other, can we have a shorter way? We do. It is what we call the crossover method. And let me show you how that works. What I'm going to do is I'm going to look at the 2 ions that are going to form the compound. Notice that sulfide here is -2, and I'm going to go there, and sodium here is +1. So if I simply take the number, not the charge, you can see how crossing them over, the charge or the absolute value of the charge of one ion becomes the subscript in the compound for the other ion. Let's do here aluminum chloride here, the aluminum and the chloride ones. Again, notice that I can take the 3 here, cross it over there, and then 1 here, cross it over there, and that gives me the formula without having to do all this analysis of charges and numbers and all that kind of stuff. For the sodium and the fluoride ions, again, we cross over there and we get 1 and 1. Now, let's look at this one here. Technically, if I were to follow the crossover method here, I would have gotten, 2 and 2. But remember that this is just an assembly of ions. It's not a unit. Therefore, what I want to express is the simplest ratio between these ions in the compound. And a 2-to-2 ratio can be simplified, right? So when we have this kind of situation, we are going to simplify. And I hope this comes across here in the colors. We're going to simplify so that we have the smallest possible whole number ratios of ions in the formula of the compound.
Okay, now that we have tried that, here are the formulas for sodium and fluoride ions. NaF, notice that we write the cation's symbol first. For calcium and oxide, that would be CaO. Remember that we keep a 1-to-1 ratio of each. For aluminum and chloride, AlCl3. For sodium and sulfide ions, Na2S. Okay, ready for another complication? Here we go. It turns out that in many common ionic compounds, the ions are themselves composed not of a single atom, but a group of covalently bonded atoms. That means joined atoms with an overall charge. This group of charged species is called polyatomic ions. Look at these 3 compounds here, NaNO3. Once we identify who the metal is, in this case sodium, we know that it must have sodium ions. But the rest of the formula, the NO3, we do not assume that these are nitride and oxide ions. We assume rather that this is an ion that has the formula NO3, and by virtue of having a 1-to-1 ratio with the sodium, it must have a -1 charge. The next one, CaCO3. Again, we identify the metal, that's calcium, and calcium must have a +2 charge. The rest of the formula, the C and the O3, are not separate atoms. They form a joint polyatomic ion, CO3, with a -2 charge. Similarly for KClO, we identify the metal first of all, that's potassium. Potassium must have a +1 charge. The rest of the formula consists of the polyatomic ion, ClO-. Here is a table of some common polyatomic ions. I am not requiring you to memorize these, but as we go along, some of them you will end up memorizing simply because we're going to use them a lot. Take a quick look at them and notice a few things about them. Notice that some of them exist like in series. You notice here ClO, ClO2, ClO3, ClO4. So that's an interesting series in itself there. Notice also that most of these that we have here, the majority of polyatomic ions are typically anions. They're typically negatively charged. And the third thing you notice here is that many of these have typically one or more oxygen atoms in it, right? These ones are called oxyanions or oxoanions. These are anions that contain oxygen and at least one other element. So although I'm not going to require you to memorize the nomenclature of these things, it's good to know some of the trends. For example, let's say you have a series of oxyanions that contain simply different numbers of oxygen atoms. What's going to happen is the name is going to relate to the number of oxygen atoms in the ion. All right. If there are two ions in the series, then the one with more oxygen atoms ends in ATE, and the one with fewer oxygen atoms ends in ITE. For example, look at the NO3 and NO2 polyatomic ions. NO3 is nitrate, NO2 is nitrite. Look at the next ones, SO4 and SO3, both with -2 charges. SO4 is sulfate, SO3 is sulfite. And again, be careful with spelling, because if you change that sulfite, that T into a D, it'll sound like sulfide, which is the monatomic anion that's derived from sulfur itself. Now, if there are more than two ions in the series, then what's going to happen is, besides the ITE and ATE endings, you're also going to add prefixes hypo and per. Hypo for less than and per for more than. So this series, composed of polyatomic ions of chlorine and oxygen, go from ClO to ClO2, ClO3, ClO4. You can see the names there: hypochlorite, chlorite, chlorate, and perchlorate. Like I said, you don't have to memorize these. Now, what you might want to do is maybe get yourself a printout or just a copy of this table. It's very useful, because what it does is it has the different nonmetals in there and all of the different monatomic and oxyanions that they all form in sequence. And so it's a good reference chart. Although when you do the nomenclature activity in our lab, I'm going to give you a different table for these. All right, so let's see, what do we do when we write formulas of ionic compounds that contain polyatomic ions? What we're going to do is we're going to treat the polyatomic ion as if it were a single entity. In other words, polyatomic ions, quote unquote, act as one. So let's say I'm going to form a compound between sodium and SO4 with a -2 charge. That's the sulfate ion. So again, I'm going to do like we did before, the crossover. Oh, let me see if I can get a better color here for our marker so we can see it again. Let's use yellow here. All right, so we have our crossover here, right? And we end up getting a compound that is going to be NaSO4. Let me erase these things here so we can see it better. Look at Na2SO4. Now let's look at the next one. Notice that there's no need for a parenthesis around the SO4. Anybody who sees the formula understand sodium is the cation, everything else together is the polyatomic anion. How about between magnesium and OH negative? Notice that when we do the crossover here, we're going to end up needing 2 of the OH minus ions. Watch the way we write it. See that? Notice the use of parentheses. I want to make sure the parenthesis surrounds the polyatomic ion. Otherwise, it will read as MgOH2 and suggest that I have 1 magnesium, 1 oxygen, and 2 hydrogens, which is not the case. What I have is 2 hydroxide ions, which is the name of the OH minus ion, and that would represent actually 2 oxygens and 2 hydrogens if I were just counting atoms here. How about this one? NH4 plus and CO3 2 minus. Again, if we do the crossover, we end up needing 2 of the NH4 ions. Again, we're going to surround it in parentheses to make sure that it doesn't read NH42CO3, right? So be careful with that. Okay, we've been talking about formulas, and I think we have an idea of how to do these formulas. Now let's look at names. How do we call these things? When you see a formula, when you assemble an ionic compound's formula, how do we say its name? Well, the way we say it is basically the cation goes first and the anion goes second. If the anion is a simple monatomic ion, we use the name of the element with the IDE termination, right? So for example, lithium and bromide ions would form lithium bromide. And if you do the crossover, you find out that's the formula LiBr. Barium and chloride ions would form simply barium chloride. Notice the formula. Cross over the 2 and the 1, and you get BaCl2. Notice that we don't say anything regarding the number of chlorides in here. Don't get it confused with the other type of compound we're going to study where we use prefixes. So we don't call this compound barium dichloride. We simply call it chloride. And because we know what the charges are, we know what the formula should be. So there's no need to put any prefixes. The only exception will be there are some polyatomic ions that their name itself contains a prefix. For example, there's a polyatomic ion called the dichromate ion. In that case, that's part of its name. It doesn't mean that there's 2 of them, it just means that's its name. Let's look at the next one here. Cu 2 plus and SO4 2 minus. Well, Cu is copper, but we look back at that table before and realize that because copper could also have been Cu plus 1, we have to name it according to the actual ion, which is copper 2, and then sulfate we get from our table. And because the crossover would technically yield 2 and 2, we simplify that to a 1-to-1 ratio and write the formula as CuSO4. Now, what about going from the formula into the name? Again, to find the identity of the ion, you simply do a reverse crossover. Let's close out this section of the lecture with a little practice. We're going to go to our paperboard for this.
What happens when the metal cation belongs to that category of transition metals that can form more than one kind of ion? How do we determine which one it is? Let's consider the compound on the top here. It has iron and it has oxygen. Of course, the metal iron would be the cation, and the oxygen will be present in the form of an oxide ion, right? So one method you can use is what we would call the reverse crossover, which is, like it says, the reverse of the process by which we would have come up with the formula starting from the ions. So this is, of course, a 1 here, and this is a 1. So it would predict, in this case, that the iron would be +1 and that the oxygen would be -1. But we know that oxygen forms an ion that has to be O2 minus. In other words, there is no oxide ion with one negative charge. So what we have to do is we have to adjust this reverse crossover by multiplying them by 2, both of them, which leaves me then with the iron 2 and the correct charge on the oxide ion, which means therefore that now this compound would be iron 2 oxide. So that is one way that you can do it. Other students prefer a different method that a former colleague of mine called the tic-tac-toe method. Okay, in this case we have tin and we have oxygen. Now we know that tin can form a +2 or a +4 type of ion. Which one is it here? Well, let's start out by writing down the two components here, Sn and O, and let's draw a little grid here. And we're going to separate it into sections. And let's pick the one that we know. Over here, we know that oxygen has to be a -2. We know this. Now, how many oxygens do we have in the formula? We have 2 of them. So this is the number of atoms of that particular component. And that means that if you multiply that out, you get -4 charges. These are the charges to neutralize. We have to neutralize 4 negative charges. So what we do now is we kind of make a little turn here. And what we're going to say is, well, that means that I need +4. This is, oops, sorry, I put this 4 too far away. Number 4. These are the charges needed in order to neutralize the -4. Now, how many atoms of tin do we have? Well, we only have 1, right? So this is number 5. This is the atoms that we have. And so what we're going to do is divide the 4 charges between those, and we arrived at what the charge on the tin should be. And that is the tic-tac-toe method. So that tells us that we have the compound would be tin 4 oxide. And just remember that with ionic compounds, we do not use prefixes. So just because there's 2 oxide ions here, we don't call this dioxide, all right? It's just oxide. The presence of a metal ion tells us that this is an ionic compound, and the formula and the name simply represent the ions that are present, and the formula tells us the ratio in which they are present.
Okay, I hope that helped. We're going to take a break now, and in the next section, we're going to talk about molecular compounds. Thank you so much.